We'll now begin our discussion on complex numbers. Some of you might be familiar with complex numbers. Some of you might not be. We all need to be familiar with them in order to succeed in this course. And so let's go ahead and start in talking about complex numbers. Now, complex numbers, they involve a term we call the imaginary number. Which, as a side note, is a terrible name for this number. There's historical context on why it was called an imaginary number. It was actually mathematicians kind of getting in a disagreement and making, quote, fun of each other, and the name kind of then stuck from that. And I mean, this is centuries ago. And so, unfortunately, we're stuck with this name for imaginary number. But you don't want to think of it that it doesn't exist. And I'll give you an example on why I mean that you don't want to think of it as it doesn't exist. So this imaginary number came about because mathematicians were interested in solving quadratic equations. And you can remember from math class that a quadratic equation is in the form ax squared plus bx plus c equals 0. Now, this is, as I said, centuries ago, they knew how to solve these quadratic equations, and they were really interested in being able to solve lots of them. And they were looking at several types, and they noticed that there were several types of quadratic equations that, given the mathematics they had at the time, had no solution. So if you look at x squared plus 1 equals 0, and we try to solve this, we would get x squared is equal to negative 1. And then x would be equal to plus or minus the square root of negative 1. Now, this frustrated mathematicians because they'd say this is, no solution. But instead, in mathematics, I like to say it's not a real solution, meaning it's not a real number, because we have what we call real numbers and imaginary numbers, which again, those names are kind of bad. You don't want to think of imaginary as doesn't exist. All right, so they didn't like the fact that they didn't have solutions for all these quadratic equations. So to kind of make us so that we would have solutions, what they defined here is they defined the imaginary number as I equaling the square root of negative 1. Now, this is something, before we even move on any further, I'm going to star this here. In EET, so EE, EET, whatever, any kind of electronics, we use J as the imaginary number. So we say that J is equal to the square root of negative 1. Now, on your calculators, it's not going to typically have J. It's still going to have I. So when we use our calculators, we're going to have to use the I. But the reason we use J is because I, in electronics, we should all know, represents current. And so we don't want to get confused as like, well, is that I representing a current, or is that I representing the imaginary number? So what we do is we'll say, okay, well, we'll just take the next letter in the alphabet, J, and for us, we'll say that J is the imaginary number. And so they did this, and now the benefit of this was that all quadratic equations had solutions. So that was great. Now, as I said, they call it imaginary, and that's really a bad name. And the reason I want to say it's a bad name is I always tell people is, let's have an example here of, display on your desk right now at home -1 pens. So a negative number. So display on your desk -1 pens. And the answer is you can't, right? We can't say display -1 pens. because that doesn't really make sense to us. Now, I've had some people in classes I've taught before where I'll say, give me -1 pens, and they'll say like, oh, well, that just means I owe you a pen. And I'll be careful to say, well, that's an interpretation of what the negative number means. That's taking that negative and applying it into a situation where it gives us information and makes sense. But -1 in itself, I don't have -1 pens in my house. I have maybe, 10, 12, 13, whatever, but I don't have -1 pens. But we're fine with negative numbers. No one has a problem with the fact that, oh yeah, negative numbers make sense. It's the same idea with the imaginary number. So j equaling the square root of -1. We might say, well, that doesn't make sense. You can't do the square root of -1. Well, we can no more do the square root of -1 than we can display -1 pens on our desk. But in applications, we can make this have meaning for us in applications to help us solve problems. And that's the exact same thing we do with the negatives. We use them to have meaning in applications to help us solve problems. So that's the key thing you want to take away here. So we've gotten enough discussion on this imaginary number. Let's move on here and really define what we're interested in, which is complex numbers. And so a complex number, I'll write it here as z. That's a fairly standard notation to let z being a complex number. And I'm going to write it as a plus j times b. And so what we want to see here in a complex number, there's what we call the real part. And then there is what is called the imaginary part. And when we refer to the imaginary part, we don't include the j with it. We just look at the number associated with it. And so as a quick example here, we might have z is equal to 4 plus j3. And then a notation that we use, we might say, well, what's the real part? And we abbreviate this RE for real. What's the real part of z? Well, that's just simply 4. And then we can do the same thing for the imaginary part, IM of z, which again, that's just the number, so the imaginary part is 3. Now, it's fine to also write this as a side note as 4 plus 3j. I just typically write my j's in front. That's just how I was taught. There's no reason you can't write it as 3j if that's the way you want to do it. Sometimes I'll flip between the two, but they're equivalent. Now, the only other thing I'm going to do here with an example on this is let's look at, for instance, maybe 5 minus j2. And it's not that this is supposed to be a challenging problem, but it's just the, let's be careful of things here. So we have the real part of this, 4, I'm going back to the previous problem here. The real part of this is 5. And then the imaginary part of z, well, this is where you have to make sure to take the negative sign with you. So the imaginary part of z is -2. Okay, so nothing hopefully too confusing or anything about that. So that's our first kind of business here with imaginary numbers or complex numbers here, is some basic ways of writing them down and the imaginary real part. There's one other thing here that we want to make sure to emphasize before we move on, and that's j squared, which we'll encounter more often than you might think, is equal to -1. And that makes sense if I just go off to the side here. If j is equal to the square root of -1, and then I simply just square both sides, well then j squared would just equal -1. But that's a very useful thing that we're going to see creep up quite a bit. So it's useful. Okay. The next thing I want to talk about is the formats that you can write complex numbers in. there are two formats that we can write complex numbers in. There's what's called the rectangular format. Sometimes some people call this Cartesian. I don't encounter that very often. It's usually called the rectangular format. And that's what we just did here. That's the way we first defined it. This is the rectangular format. And then there is what's called the polar format. And this is written where we have some what we call magnitude, z sub m, and we use this angle symbol, and we say it's at an angle of theta. So this is the magnitude and this is at the angle of theta. And it's going to be important to be used to both formats. We're going to use both formats in the course, and then sometimes one format's preferenced above the other one because some computations are easier to do in polar format and other computations are easier to do in rectangular format. Now, to really illustrate how these two formats are related to each other, it's useful to just have a graph here to kind of illustrate this. So what I'm going to do is I'm going to just draw a simple xy plane, but instead of having this be x and y like we're normally used to doing, what we're going to do here is we're going to call the x-axis the real axis, and we're going to call the y-axis the imaginary axis. And then we can actually plot imaginary numbers now. And so as an example, let's look at the imaginary number z equals 5 plus j2. So the real, we want to think this is kind of this 5 is my x direction, and this positive 2 is my y direction. So if I were to plot this, I'd do, okay, well, 1, 2, 3, 4, 5, and then up 2. So this would be my complex number z equals 5 plus j2. So that's one way to locate it. We can just go over 5 and up 2. So that's one way to locate where that complex number is. But another way to locate it is kind of using vectors where I have this line here, and I can say, well, what's this distance? Well, that distance here is what I had labeled as z sub m, and then we can see, well, wait, there's an angle here of theta. So I can say, how much should I rotate from the x-axis? In other words, maybe I say, okay, first go out a distance of zm, then rotate up by an angle, or rotate counterclockwise by an angle of theta. That's another way to get to the same point. So two different ways to describe the complex number, both getting us to the same point. Now, I'm going to actually end the video here, and the next video we'll talk about how do we go between these two notations. It's going to be useful for us to be able to convert between the rectangular and the polar format.